In this class I want to introduce the concept of correlation and talk about the ways in which we can measure the association between sets of numbers. Let's take three sets of numbers, x, y, z. Now, is there a relationship between the sets? That's the most basic thing we can ask. And are the sets the same or are they different? And does x influence y, or does x and y influence z? I mean, exactly what is the relationship between these three sets of data? Now here we should note immediately that we're looking at association between the numbers, not causation. We're not saying that x causes y or x and y cause z or whatever. We're not talking about causation, one causing the other. We're talking about association. That as x varies, let's say y varies. It's a statistical relationship. Causation requires extra work to try and determine what exactly is causing it. What is the causal link? We're looking at association in numbers, which may suggest causation, but it may not as well. So we're just looking at association between numbers. Not saying that one causes the other, we're just saying they are, chances are they're linked in some way. And we can do this by looking at correlation. We can look at the difference among paired samples, and we could use regression. So there are various techniques we can use. In this particular session we're going to talk about correlation. Now, correlation is a single number that describes the degree of relationship between two variables. And the single number is called the correlation coefficient. It varies between -1 and 1. So it could be -1, or it can be any number between -1 and 1. So it includes 1 and -1 and any number in between. We'll talk about the importance of those numbers in a second. Now, a positive correlation, if the values of one variable increases and the value of the other variable also increases, then we'd say there's a positive correlation. If the two sets of numbers are increasing, let's say, there is a positive correlation. Or if both sets of numbers are falling, both are falling together, there is a positive correlation, because they're moving in the same direction. If both are falling, they're moving in the same direction, so it's positive. A negative correlation is when one set of numbers starts to increase and the other one, let's say, stays the same or decreases. Generally speaking, decrease. So as one set increases, the other set decreases, that's a negative correlation. Actually, if the numbers didn't move, if one set stayed the same, as I suggested earlier, that would be a zero correlation. But that situation is when the correlation coefficient is equal to 0. It should also be worth noting here that we are talking about linear relationships. We're assuming that there is a linear relationship between the two sets of numbers. Now, many numbers can be linked, and there's not a linear relationship. There could be a different type of relationship. They're still linked, but correlation coefficient will not pick that up. So it only picks up linear relationships. No correlation is when the two sets of numbers, they don't move together. One moves up, the other moves down, then it moves up again and it moves down again, and so on. So there's no particular, it's almost randomized. There's no particular relationship between them, in which case the correlation coefficient would be 0. A perfect correlation is when the numbers are 1 or -1. In this case, as one set of numbers, let's say, increases, the other set increases by some proportion. Let's say one set of numbers starts to double and the other set of numbers starts to double. Now, that means there's a perfect positive relationship. Or if one set of numbers starts to double and the other set of numbers starts to halve, there is a perfect negative relationship. So if one set of numbers is, let's say, increasing and the other set of numbers is decreasing, but it's decreasing following the same rule, if you like, then it is a perfect negative relationship. So the summary, well, correlation coefficient varies between -1 and 1 inclusively. So it can include -1 and it can include 1. The closer to -1, the stronger the negative linear relationship. The closer to 1, the stronger the positive linear relationship. The closer to 0, the weaker any positive relationship. Probably the best way to illustrate all of that is by looking at some pictures. Let's look at the first one here. Put the cursor onto the screen. Let's look at this one here, X and Y. You can see here that the observations are falling in a straight line, falling downwards, but they're all falling along the line, in which case the correlation coefficient is -1. Over here on the bottom, they're all increasing. They're all on the line, but they're increasing, so the correlation coefficient is +1. Here's -1, +1. That's what it would look like. More generally, we find a scatter of observations like this, and we put in the regression line, or the line of best fit, in here, and you'll see that some lie above it and some lie below it, and what the correlation coefficient does is it measures how well this line fits the data. In this case, because it's sloping downwards, we have a negative correlation coefficient of 0.6. And down here, this diagram down the bottom, here it's very loose relationship. All of the observations are quite a bit off the line and so on. So it's weak. It's positive, it's moving upwards, but it's very weak. So you say it's positive, upward sloping, but 0.3. When it's calculated, it becomes 0.3. And over here, the observations are off the line, but as x is I should say y is a constant here, and x is varying. Well, there's no relationship between them then. So it's 0. X is varying, but y is a constant. Y is fixed at this level. And even if the observations fell along the line here, it's still 0. It's still y is a constant and x is varying. X is small, x is large over here. So it's varying, so there is no relationship. Now if we look at a calculation here, let's say we have people in a class, just pretend, and let's say we have 20 people in the class, and we measure their heights in centimeters. And we also have some sort of index, psychological index, for measuring their self-esteem, how they see themselves. Now if we chart these, we'll find this arrangement here. It's a bad chart because we can't really see what's happening along the self-esteem one. It's just bouncing along the bottom here. You can't really see the variations in it. It looks like almost a straight line. So it's not very good. And this one up here is way up here. The difference between the two, of course, is enormous. This one is 68, this one's 4.1. 71, 4.6. So there's a big gap in between. Here's the gap. So we want to see how these two variables are linked. What we really need is both of them to make sense on the chart. Well, one way of doing this is to index all of the numbers. So we can pick any person along here. Let's just pick person 13. It could be any person, doesn't matter. So we'll pick person 13 who's got a height of 63 centimeters. Now if we divide all the others by 63, we'll get an index. So 63 divided by 63 is 1. 67 divided by 63 is 1.06, sorry, 1.06. 68 divided by 63 is 1.08. So what we've got here is it's the same set of numbers, except we've just indexed it all by one of them here. It's by 63, let's say. So that's our new refined set of numbers, our index numbers. And we can do the same for self-esteem. We take the same person here, 3.7, we divide 3.7 by 3.7, we get 1. 3.2 divided by 3.7, we get 0.86. So now we can index all of those. And when we chart this new set of numbers, this index of heights against index of self-esteem, we'll get this chart down here. That's much better, much better than the previous one. The previous one, you couldn't really see the variations in self-esteem. Now you can. Now you can see it's moving up and down. And you can see that as the heights move down, up, down, self-esteem tends to up. It's up here, but never mind. It's down here. It's up here, in line with the heights. It comes down. It goes back up. It's not perfect, but it seems to be a pattern nonetheless. It's somewhat worked out. In fact, if you worked out the correlation coefficient here, you'd find it was 0.73. Now, in statistics, a correlation coefficient of 0.7 or above is generally agreed to be a good figure. There is a good relationship in the numbers. So 0.7 and above that's a good figure. So there is a relationship, a statistical relationship between these two sets of figures. That's what this calculation is telling us. 0.73 is acceptable. Anything above 0.7 is acceptable. And that will be calculated using the correlation formula, or you could use computers to calculate it. I suppose it's important to see how it could be calculated using the formula. That is actually the formula. We're not going to use it here, but that's how you would calculate it using the formula. And I suspect that will cause a lot of sleepless nights. However, as I said, we won't be using that. What we can do is we can use a spreadsheet. I tend to use Excel in Microsoft Office, but if you haven't got Microsoft Office, OpenOffice, which is a free download, and there are several, in fact, free downloads you can get of Office suites. The spreadsheet in those will do this. Many of them are excellent and will do this calculation, and will do it the same way as I do it in Office. So the easiest way to do it is on a spreadsheet, and that's what we'll come back to do in a different video. But that's all I want to say about correlation coefficient at this moment. It's just a brief, simple introduction to what a correlation coefficient is. And I'm going to leave it at that, so thank you for watching.